Okay, in this video, we're going to look at some examples of predicting products of E2 reactions. Okay, so we want to predict the major and minor products of the following E2 reaction. And so, right, in our E2 reaction, we're going to lose the halogen, and then we're going to lose a hydrogen on one of the beta carbons. So in order to predict the products, I need to know where I have hydrogens on beta carbons. And so, right, this is a methyl group. So I've got hydrogens there. I've got hydrogens there. I've got hydrogen there, and those are my only beta carbons. Now, these two methyl groups are chemically equivalent, so it doesn't matter whether I take one of these hydrogens or one of these hydrogens, the product is going to be the same. And so if I take one of those, my product is going to look like this. And then, right, there are two hydrogens coming off here, so I don't have to worry. This doesn't have cis and trans or E and Z isomerism. My other product would be to take one of these hydrogens and the bromine, so I get a double bond here. So my other product would look like this. And again, right, the two groups coming off this carbon are both methyl groups, so I don't have cis and trans isomers. So now I need to decide which one is the major product and which one is the minor product. So hydroxide is not a bulky base, and so if you remember our video on alkenes, more substituted alkenes are more stable. And so when I have a base that's not bulky, it's going to prefer the constitutional isomer that is more substituted. So because this one is tri-substituted, whereas this one is di-substituted, this is going to be my major product, and this is going to be my minor product. Now, just a note on terminology. If you watch the other video on E2 reactions, the more highly substituted product is called the Zaitsev product. The less substituted product is called the Hofmann product. Okay, so this is the same substrate that we had in the previous example. The difference being I've changed my base. But the two possible products are going to be the same. Now the difference is, in the previous example, hydroxide was our base. Now we have this T-butoxy ion as my base. Right? And so when we have these big bulky bases, they actually tend to prefer the less substituted or the Hofmann product. And so in this case, with the bulky base, this is going to be my major product, and the Zaitsev product, the more substituted alkene, is going to be the minor product. Okay, here's a new substrate, and so I need to identify where do I have beta hydrogens. And so here's a beta carbon, but it's got all carbon-carbon bonds, so I got no hydrogens here. So this is the only beta carbon that I can get elimination from. Right? Now it has two hydrogens, so it's not going to be stereospecific, so I don't have to worry about that, but it is going to be stereoselective, and I think I'm going to be able to get both the cis and the trans isomers when I make this double bond. So my products I'm going to be lazy. Rather than drawing the whole benzene, I'm just going to write pH for phenyl group. And then I can get the T-butyl group. So this would be the trans, because the hydrogens are across from each other, or the E isomer, because the higher priority groups are across from each other. But I can also get the cis, or in this case, the Z isomer. And so this is an example of a stereoselective reaction where I can get two different stereoisomers, and we want to know which one is more likely. And so the difference between these is here I've got these big bulky groups across from each other, in the trans or E configuration, and in this case, the two big bulky groups are on the same side. And so this product is going to be more sterically hindered. So the first one is going to be my major product, and the second one is going to be my minor product. Okay, here's another example. And so I need to identify my beta hydrogens again. So I've got a methyl group here. So I can lose hydrogens from there, or I have one hydrogen on this guy. And right, he's essentially coming out towards me. So the first product I can make, if I pull off one of these guys, is going to give me this product, and then right, I've got two methyls coming off here, two hydrogens coming off here, so I don't have to worry about cis and trans isomers. When I pull off this hydrogen, now I have to be a little bit more careful. So this is an example where we have stereospecificity. So there's only one hydrogen on this beta carbon, and then this carbon is also chiral. And so when we have this situation, it's going to be stereospecific, right? So when I have one hydrogen on the beta carbon and both alpha and beta carbons are chiral centers, we have to worry about stereospecificity. And so only one isomer is going to be produced. And the bromine and the hydrogen have to be anti-periplanar from one another, right? They've got to be, essentially what we want is we want the bromine, the hydrogen, and the two carbons to all lie in the same plane, right? So what we really want is we want the bromine here, and we want the hydrogen coming off here, so that then they would all be in the same plane. And so I have to rotate around these single bonds in order to get that configuration. And so, right, this bromine, we also have a hydrogen coming off on a dash going away from us. And so what we're going to do when we rotate it, so the bromine is going to take the place of the methyl is going to take the place of the hydrogen, and the hydrogen is going to take the place of the bromine. So we're going to kind of rotate it like this. And so if I redraw that, so we haven't done anything with those guys yet, but now we've rotated it so that the bromine is down here. The methyl group is going to take the place of the hydrogen, and the hydrogen is going to take the place of the bromine. And now we need to do the same thing at this carbon atom. And so we need to rotate it so that the hydrogen takes the place of, oh, I forgot carbon there, right? We need the hydrogen to be in this position. So then the methyl is going to take the place of the hydrogen, and the ethyl is going to take the place of the methyl. And so when I redraw that, right, the first carbon didn't change. Now we have the hydrogen here. The methyl is going to take the place of the hydrogen, and the ethyl is going to take the place of the methyl. And so now my bromine and hydrogen are anti-periplanar, and so now I can go ahead and eliminate those guys, and I'll get the double bond here. And you can see, right, the ones that are on the wedges are going to be on the same sides, and the ones that are on the dashes are going to be on the same sides. And so my product is going to be, sorry, I forgot the H here. So the wedges will end up on the same sides. So we've got the hydrogen and this methyl, right? So the hydrogen and the methyl are on the same sides. And then the same carbon that has the hydrogen is going to have the CH3. And then the side that had the CH3 is going to have the ethyl. And so this is going to be our product. So this is probably the hardest aspect of these E2 reactions. And when they don't draw it so that the leaving group and the hydrogen are anti-periplanar, we've actually got to rotate these guys to get them that way. And so this really takes a lot of practice. And so in addition to this example, I'd recommend look at the example in the textbook as well. Okay, and with all of that work, I almost forgot to assign which one of our products is the major product and which one is a minor product. Right, so here is our first product. Let's go ahead and circle that guy. Right here is our second product. And so to determine which one is the major and the minor product, I think we're going to go with the difference between these two is in how highly substituted they are. So we have a monosubstituted alkene here versus a tri-substituted alkene here. And so I think this one is going to be our major product, and this one is going to be our minor product. In this example, we're looking at elimination from a substituted cyclohexane. If you remember from the E2 video on stereospecificity, the requirement for elimination to be possible was that the leaving group and the hydrogen that's being eliminated had to be on opposite sides of the ring. So in this case, because the chlorine is on a wedge, in order for a hydrogen to be eliminated, it's got to be on a dash. Now, if I think about eliminating from this carbon, it's no problem, right? Because I have a CH2 here. Right, and so one of them is going to be on the wedge, and the other one's going to be on a dash, and so the elimination is no problem. Now, in this case, on the right, I have a methyl group on a wedge, but that means that there's a hydrogen on a dash, and so I'll be able to do an E2 reaction where I form the double bond either here or here. If this methyl group had been on a dash, then the hydrogen would have been on a wedge, and I wouldn't have been able to make the double bond here. But in this case, because the chlorine and the hydrogen are on opposite sides of the ring, I can do the elimination on this side. So in this case, my two products are going to be this compound and this compound. And then to decide which one is the major and the minor product, in this case, I have a bulky base, and so the less substituted Hofmann product is going to be favored. And so in this case, this will be my major product, and this will be my minor product.